Any questions from last time or any time?
Yeah, I have a question about one of the problems I was working through on the handout sheets.
Okay.
It's from the first gas law set of problems. 7.16. I have it pulled up here if it's easier for you to reference them or.
Okay, which one?
I guess it's about 3 of them. Maybe my approach is just wrong.
What section is it in?
Section 1,
Okay,
on the first column, that bottom third problem,
okay,
and then on the right column, the top and bottom problems.
okay.
My
Alright.
answers didn't match what was on the sheet, and I didn't understand if maybe I was doing something wrong.
Okay. So 50 milliliters of H2SO4 is titrated with 40 milliliters of 0.20 molar concentration of NaOH. What is the molarity of H2SO4?
Is this not just M1V1 equals M2V2?
No.
That's where I went wrong.
And the reason it's not is because we're dealing with two different substances. So that M1V1 equals M2V2 is referring to diluting a solution. So it's the same solution, we're just adding water to it.
Okay, I see.
Do you want to go through this one?
Sure.
Okay?
So then does it involve writing a balanced equation of the two?
Yes. So this is a titration problem. Titration means what? We're dealing with an acid-base reaction that is neutralizing. So what's the acid in this problem?
H2SO4.
Good. H2SO4, and what's the base?
Whatever the other one is.
Yeah, NaOH. This is a double replacement reaction, so we're going to get water and sodium sulfate. We good? So we got to have a balanced equation. How do we know we have to have a balanced equation? We're going from one substance to a different substance. So we have to end up using the mole-to-mole ratio. So if we balance this, we're going to put a 2 right there and a 2 right here, and we should be good. Okay so far? Now we have this substance and this substance. You can kind of separate them, the quantities you know about each material, each substance. Start with the substance you know most about. Because we just start with what we know, but we do know 50 milliliters of H2SO4, but we don't know its molarity. If we're looking for molarity, that is moles over liters. We can have liters pretty quickly, right? So we just need moles of H2SO4 and we got it. Does that make sense to everybody? Okay. So if we need moles of H2SO4, then we have a lot of this stuff. So if we find moles of NaOH, we could then use the mole-to-mole ratio. Y'all with me so far? Okay. So we're going to start with this over here. I'm going to start with 40 milliliters. Why? Because that's the simplest component. Just remember, molarity is moles over liters. So whenever we use that as a conversion factor, change it to moles over liters. We're going to convert milliliters into liters because we have liters over here, right? So 1,000 milliliters to 1 liter. And we're dealing with NaOH so far. Better put that in there. Okay. Now I can, so I use that, I'm not going to use that again. Now I can use the concentration of NaOH, and I'm going to have 0.20 moles of NaOH on top and 1 liter of solution on bottom so that liters go away. Okay so far? Now we can use the mole-to-mole ratio from NaOH to H2SO4, which is a 2 moles of NaOH to 1 mole of H2SO4. And now we have moles, but we're looking for molarity, so I can just divide by liters. I can convert that to liters first, or I can just throw it in the mix, whatever you'd like. 50 milliliters is the same as
Just do
0.05 liters. Yeah, so we can just convert this 50 milliliters, 1,000 milliliters to 1 liter, and that gives us the 0.05 liters. So now we divide by 0.05 liters, and now we have moles over liters. That's what we're looking for. We have the right substance. That's it.
Is the 0.20 M of NaOH? I guess, well, no, that's not moles, it's molarity.
Yeah,
Moles and molarity are not equal.
that's right. This is moles over liters. And when we stick it in as moles over liters. And if we wanted the moles to cancel, we'd just flip it, right? Does that make sense?
That does make sense. I would have approached it differently and just converted it straight to moles, maybe? Because that just seems,
Yeah. So could we have started with this instead?
yeah.
Sure. If we just kind of flip those around, but we still have to convert that to liters either way. So yeah, either way works.
I think we can think of it like molarity equals moles over liters. We have molarity and we have the liters, but we need moles. So we just multiply the molarity by the liters.
And that works too.
Is that what we did?
Yep. Yeah. So I started with 40 milliliters. Do you have to start there? No, you don't. So if you like your way better, yeah, do it. Do it, no problem. As long as we know what we're looking for, the units crossed out appropriately until we end up with the units that we're looking for. That's it. That's dimensional analysis. A lot of different ways to do it.
So we found liters, but do we know how many moles we have?
So from this part right here, liters cancel, we could find moles of NaOH. But then I just continued and did the mole-to-mole ratio. And then once I had moles of H2SO4, I just divided by liters of H2SO4 solution, and that got me molarity. Do you want to find the answer, or are you good?
No, I'm good.
Okay. Anything else? All right. Yeah, always come with questions. Sometimes it feels like we just cram through everything, but make sure we understand what we're doing. All right, let's move on. We had one example problem we didn't cover last time for, yeah.
Sorry, one more question.
Huh?
When discussing gases, I'd just like to know what units to expect for each
Okay.
variable I'm working with. So we spoke about temperature always being Kelvin.
If we're using this equation, PV equals nRT, pressure is always measured in ATM,
Okay.
volume's measured in liters, moles is moles, and temperature is Kelvin.
Otherwise, we have to worry about R being a different
Yes,
value, right?
that's
Okay.
if R is equal to 0.0821, and that is ATM liters per mole Kelvin. And you're given this value on your reference sheet, so if you forget what the units are, refer to that.
Are we given conversion factors between the different types of pressure? Millimeters? of
Great
HG
question.
and
Let's see.
PSI and Pascal?
I don't think so. So you better put those on your other reference sheet. Yeah. Anything else? All right. So who can remind us what specific heat capacity is? Yeah,
That's like how much energy it takes for the change 1 degree.
to change 1 gram of a substance by 1 degree Celsius. Yep. So specific heat capacity is specific on how much mass we have. Heat capacity is not specific on how much mass we have. So like the two pans that we talked about, right? The larger pan has a larger heat capacity because it's bigger. But they have the same specific heat capacity because it's how many joules of energy is required to change 1 gram of that material by 1 degree Celsius. Good? All right, so just to remind you the equation, we got the amount of heat, or Q, is equal to mass times specific heat capacity, which is little c, times delta T, which is a change in temperature. Remember, change in temperature is equal to what again?
Final minus initial.
Final temperature minus initial temperature. We good? All right, let's do an example. How much heat is required to raise the temperature of a medium-sized pan with a mass of 2,500 grams by 50 degrees Celsius. So the things we have to know is the specific heat capacity, if in this case it's an iron pan, is 0.449 joules per gram degree Celsius. What else do we know here?
Is that big C or little c?
That's little c. And how we know it's little c? Because it has a unit of grams in there.
Oh.
But yeah, it's hard to tell the difference between a big C and a little c if there's no other letters by it. Okay? What is the 50 degrees Celsius? Good. It increases, or it raises, let's see, to raise the temperature by 50 degrees. It doesn't say it has to be 50 degrees, right? It just increases by 50 degrees. So a change in temperature is 50 degrees Celsius. And of course, we have the mass of our pan is 2,500 grams. So just kind of like on the last problem we did that Victor brought to us, we can only use this if it's the same material. If we're talking about two different substances, we can't just use one equation, okay? So the specific heat capacity, this equation right here, is referring to one substance. All right, so now we can find Q. The Q is what we're looking for, right? How much heat, that's Q, is equal to the mass of our pan, which is 2,500 grams. And we are in the right units because our specific heat is joules per gram degree Celsius. And our change in temperature is in degrees Celsius, so we're good. multiply specific heat capacity to 0.449 joules per gram degrees Celsius times change in temperature is 50 degrees Celsius. So just make sure that your units cancel appropriately. And we're left with joules. Good, that's what we're looking for, heat energy. And we get that our Q, our heat is 56,125 joules, or we can rewrite that as 56.1 kilojoules. Yeah, yeah.
0.449, that's a constant that we'll always use?
That is what we use for iron.
Oh, okay.
Do you have to memorize that? No, there's a whole bunch of charts with these values on.
So that'll be given to us?
No, you have to have that book I'll give that to you. Yes, I will give you that. Or you'll have to determine what it is, right? So if I give you everything, I give you the amount of heat, then you can figure out the specific heat capacity, right?
Okay.
Good. Any questions on that?
Why did we not change the, never mind.
Good?
I was gonna say the grams to kilograms.
Yeah, we don't because the units cancel appropriately. And that's how you know when you do. So if nothing else, just plug your values in, just make sure you have units and use dimensional analysis. Good? Yeah, Victor.
What are the unit differences between big C and little c? It's joules per grams Celsius or
Joules per degree Celsius. So heat capacity is just joules per degree Celsius. It doesn't depend on how much you have.
Okay.
It just depends on what the object is. So that larger pan has a greater heat capacity than the smaller pan. Because it can hold more energy before it raises the temperature of that object by 1 degree Celsius. Rather than the specific heat capacity is to raise 1 gram by 1 degree Celsius.
Okay.
Yeah, they kind of sound the same and they look the same, but they're just different because of that mass difference. Good? All right, we will go through some more of these, so unless you really, really want one of these, another example of these, so we're going to go through tons of different kinds of examples of using this equation. Okay?
Are those all in the sheets? You can use this equation, solve these?
You use the, well, yeah, how do you know what equation you use? That's a great question.
I'm gonna give you the same information and everything, but they're asking us for.
Okay, here's how you know what formula you use. First of all, you write down what you know. And see how I wrote it down like this? I didn't just, oh yeah, I have a number right here and I have a number right here and I don't. Write down what you know with our symbol. So C, specific heat, is 0.449 and use your units, joules per gram degree Celsius. Change of temperature is 50 degrees Celsius and mass is 2,500 grams. Then you find the equation, okay, and we're looking for heat. We got to know what we know, and we got to know what we're looking for. Then you find, okay, is there an equation with all of those items in it? And if there is, makes your life easy. If there's not, you might have to find something else first, right? For example, what if we didn't know the temperature here, but was given the pressure, the volume, and the number of moles, and it was a gas,
You can use the.
right? Okay, but this isn't a gas, so we won't use that here. Any other questions? So I know some of these problems could be overwhelming, but if you just follow that problem-solving strategy, write down what you're looking for, write down what you know, and start with what you know, or find an equation that has all that stuff in it. And we have a lot of equations, so just refer to that reference sheet on every problem until you get good at these things. Because sometimes we'll use two different concepts to solve a problem. So you kind of have to do this one first before you can use this one. Okay? Any other questions? All right, we're going to move on to calorimetry, which calorimetry is just a way to measure how much heat is transferred. Really, what they use it for is to determine the specific heat capacity of materials. And all that's done for us. So now, so really, it seems like the last part of this class feels like practicing our math, right? Or our algebra. And that's a lot what it is. But more than that, I would say it's helping us practice problem-solving strategy. If you guys can use that, especially in engineering, other sciences, that is so useful. You can solve any problem you want if you have that down. Okay? And it doesn't have to be math either. It could be any problem, really. Okay? All right. We ready? Okay. So a calorimeter, let's just, here we go. It's a device used to measure the amount of heat transferred. Transferred between the system and its surroundings. So here's an example of where we could use it. You know how you buy a packaged food and it has nutrition facts, right? And what does it always give you on those labels? How many calories, right? Because our diet says we can only have 2,000 calories, whatever, right? But how do we get that? With one of these things, okay? Kind of ish. But if you got to have something to contain that heat so that you know exactly how much heat you got. If you just did it out in the open, where does that heat go? Whoosh, everywhere. And it's harder to measure how much heat was created by that reaction. So you put a chemical reaction in one of these things, and you can determine how much heat, therefore convert joules into calories, and then you can throw it on your food label and sell it, right? And if it has too many calories, then you adjust your recipe and so that more people want to buy it. Okay? But that's just one little teeny example you could use it for. All right. I didn't finish this. Transfer between the system and its surroundings in a chemical or physical process. So we're going to start with physical process. Why? Because that's simple. We're going to start simple, but then we'll end up with doing it with chemical reactions. Okay? So the equation we use for this is Q equals MCAT, or MC delta T, the one we just started with. Now the thing that we got to know here is the law of conservation of energy. This is the first law of thermodynamics. What is the law of conservation of energy state? Anybody know? Yeah.
And then it cannot be destroyed or created.
Yeah, energy cannot be created or destroyed. Energy, and you said mass, but mass is definitely part of that. Okay? So you think of Einstein's equation equals mc squared. When you take a substance that decays into another substance, it loses mass, then what? It gives you a lot of energy. So that law of conservation of matter is tied to the law of conservation of energy. So energy just transfers from one to the other. So if we have an equation that states that, it's simple. Q of the system, so amount of heat you have in the system is equal to the negative heat in the surroundings. So does the surroundings always have to be the negative one? Or can you flip it? What do you think?
By negative, we can flip it.
Yeah, we can flip it. Because so sometimes the system loses energy, right? And system loses energy during an exothermic reaction, then this one would be negative. So it doesn't really matter which side is negative. Just say one side is negative. Good? Why does it have to be negative? Here we go. Let's Q of system, and we're going to add Q of surroundings next to it. Now what does it equal? 0. 0 change in energy. We can't have a change in energy in the entire universe. Whatever energy we have to begin with, that's how much we have to end. We cannot destroy it. We can't get more of it. Okay? So basically that's it. But we'll just keep it in this form. Good? So another way you can think about it is whatever energy is lost by the system is gained by the surroundings, or vice versa, right? Okay, now we have 4, 5, 6, 7 examples before we talk about something new. Whew. You ready? And these examples will be a little bit different each one, but it's using the same idea, okay? Or should we just do one and you guys can figure out the rest? I'm just teasing. Okay. So example 1. Metal initially has a temperature of, so the initial temperature of our metal, is that okay, Tim? Okay. Initial temperature of the metal is equal to 90 degrees Celsius, and it's submerged into 425 milliliters of water. And the water has an initial temperature of 22 degrees Celsius. The final temperature of the water is 42.7 degrees Celsius. We want to know, what is the mass of our metal? Now we have to know a couple of things before we can do this. What do we have to know? Specific heat capacities, right? So when you get into real life, you look these values up, right? But in this class, we'll give that'll be given to you, unless that's what it's asking you to find. So the specific heat of our metal is 0.449 joules per gram degrees Celsius. Anybody know what kind of metal that is? Oh yeah, we just did this in the last problem. It's still iron. But again, you don't have to know that. And the specific heat of water is 4.184 joules per gram degrees Celsius. And we use that one quite a bit. well, especially in calorimetry, because it's, well, we fill. So let me just kind of explain how we use a calorimeter. So basically we have, and this is a cheap version, and we can buy a more expensive one. But we have a cup right here, maybe a styrofoam cup, and we have another styrofoam cup inside of it. So right in here, this is vacuum. Well, maybe not pure vacuum, but kind of like a thermos, right? You guys that's kind of how a thermos is. Keeps your stuff cold or hot, whatever's inside of it, right? Keeps it the same temperature. So we don't, now do we lose zero energy from this system? No, it's not perfect. Nothing we make here on the earth is perfect. So anyway, we also have a thermometer in here. So we got a thermometer sticking out. I'll just label that's a thermometer, not a straw. Okay. And then we have water in here. And we get a piece of hot metal, very hot, and we throw it in there and put the lid on so that no heat escapes. And then what does that hot metal do? It warms up the water, and at the same time it cools down the metal until what? Until it reaches equilibrium. So whatever heat was lost by the metal is gained by the water. Does that make sense? The water is the surroundings, the metal is the system. Are we good? Okay. So now that we have this, we know our equation is Q of the metal equals negative Q of the water. And again, it's like, oh, which one is the system? Which one is it? Doesn't matter. It really doesn't matter. One of them's negative, one of them's positive, right? And so if we put this in using our equation that we learned up here, this one right here, then we can say the mass of the metal times the specific heat of a metal times the change in temperature of the metal is equal to a negative mass of the water times specific heat of the water times a change in temperature of the water. Yeah?
You're saying, Professor, it doesn't matter which one's negative?
No, it doesn't. It'll all come out in the end. Okay? Because if we're trying to find the mass, will you ever have a negative mass? You won't. Okay? But should we flip it just to show you?
Sure.
Okay, yeah, let's do it. We're going to put that negative over here. Okay? Yeah.
Should we put like parentheses so we can like distribute the negative to every term? Or
Great. How many? No, that's great. No, you caught yourself, but that's okay, yeah. Great thinking. But there's only one term, right? Because you multiply them all together, and it's just like a negative one multiplied all those things, right? Yeah, good. All right, so let's plug some values in, or should we solve first? Yeah, let's solve symbolically first. We're looking for the mass of the metal. So let's divide everything by, should we include that negative? Should we get rid of that negative?
Yes.
Yeah, we don't want it there. Minus CM, change in temperature of M to both sides. That goes away, and we're left with mass of the metal on the left side. And then we have all of this on the other side. Rather than rewriting it again, I'm just going to plug my values in now. Sound good? So mass of the water, which is, I don't have the mass of the water, so what do I need? Density of water. Anybody know what density of water is? This is a good one to just know. 1 gram per centimeter cubed. Oh, we never use centimeter cubed. What can we call that?
It's the same as
Milliliter, right? So we can just get rid of that stupid centimeter cubed and call it milliliter. And it's more useful for us, okay? Because centimeter cubed is the same as a milliliter, okay? We good? All right, so now we can use this right here, 425 milliliters. Use the density, 1 milliliter to 1 gram. So how many grams do we have? 1, right? 1 gram to 1 milliliter. It's just a 1 anyway. So whatever milliliters we have, that's how many grams we have. So that, don't always think the volume is the same as grams. It's not. Okay, so you got to look at your units. So the mass of the water, which is 425 grams. Specific heat of the water is 4.184 joules per gram degrees Celsius. And change in temperature of the water is, oh, I don't know that. But change in temperature is just final temperature minus initial temperature. So we can calculate that quickly. And we get a change in temperature of 20.7. Let's see, is that right? 20.7 degrees Celsius. Any questions so far? So we had to find a few things before we can actually plug it in the formula. No questions? All right. Then we're going to divide that by a negative value. And the specific heat capacity of the metal is 0.449 joules per gram degrees Celsius. And the change in temperature, we got to find that over here. It's still final temperature minus initial temperature. Is that the same thing we did over here? No. The initial temperature over here is 90. What's the final? Oh, does it tell us? Does it tell us the final temperature of the metal?
They're in equilibrium.
Yes, they are in equilibrium. So they're the same temperature at the end. So the final temperature is 42.7 degrees Celsius minus a 90 degrees Celsius. And we get something, negative 47.3, right? Now what happens to the negatives, guys? A negative and a negative goes away. Do you see it doesn't matter? And if we would, well, no, you didn't see because we didn't do it the other way yet, right? But it works out. It works out to get a positive mass, and good, we need a positive mass. Oh, now we do all of that calculation, and we get the mass of the metal is 1733 grams, or 1.73 kilograms. Is that too messy for you? Because there's another way to do it. Anybody want another way? Okay. We can calculate the heat for the metal or the heat for the water because they're the same. So in this case, what can we calculate? The heat for the metal or heat for the water? The water, because we don't have the mass of the metal. So you calculate the heat for the water, and then you just use another one of those same equations, but now you know the heat for the metal. You just change the sign, right? Because whatever you get for the water, it's negative that for the metal, yeah.
Wait, I know you said this, but how do you know that the final temperature of the metal
It,
is the same as?
okay, so think about this. We have a pan of water on the boil. we're gonna cook spaghetti, because we just want something quick and simple, right? So you put it on the boil, and then your friend calls up, hey girl, we're gonna go out to eat, you wanna go with us? And you say, okay, yeah, we're gonna go out. So you shut off the heat, and then what happens?
Well, it's cold.
That hot water is hotter than the environment. When you get home, is it gonna be super hot at home? No, it's not, because it dispersed out throughout the whole house, and you're not gonna fill it. But the temperature of the water is now room temperature. It reached thermal equilibrium, and that's what happens in all cases. Well, I shouldn't say all cases that I can think of. Right? And so since they're in equilibrium, they do have the exact same temperature at the end. And how do you know it's in equilibrium? Because you look at your thermometer and it quits falling or quits rising, right? And it stops. And so if you was to do this, that's how you'd know you're done. As soon as that temperature stops changing, then you record it, and then you can calculate to figure out how much heat you lost or gained. Good? Great questions. Any other questions?
Can we say that the final heat is for the system, like for the whole system, like not only the water? Like can we say it's for the water and the metal itself?
You got to keep each substance separate. So this equation right here that we use, this Q equals MC delta T, that is for one substance only.
Yeah, but I just mean like the final temperature.
Oh,
It's
the temperature?
yeah. It's
Oh, I
like
thought you
the
said
final-
heat.
The final temperature for the water is like that amount. Can you say it's also for the for
Yes.
the whole system, not only?
In this type of problem, yes. Uh-huh.
So we could assume it's like a mixture, right? We drink metal into water.
It's a heterogeneous though, because we could easily pick that metal out. But yeah. Uh-huh. We good? Anything else? All right, you ready for a different type? Or same equation, but a different scenario? And this worksheet you picked up is basically a bunch of each scenario practice. Okay? So, and that's almost all we're doing today. We got one little other thing with the heat capacity. So this is using specific heat. There's another type of calorimeter that uses the heat capacity value. And we'll get to that at the end. All right, so let's do another example. So this time we want to determine what the specific heat of our metal is. And rather than writing this as a story problem, you guys okay if I just write down what we know and what we're looking for? Just to save a little bit of time? Okay? But to get practice, all of these are written as a story problem. Okay. Does anybody want me to write all the words out? All right. So we know the mass of the metal this time is 550 grams. And we know the initial temperature of the metal. So I'm going to write my metal on this side, and I'll write my water on the other side. Is 110 degrees Celsius, and the final temperature of the metal is 42.7 degrees Celsius. Is it always going to be 42.7? No. Okay. Happened to be in these last two problems. So there's our metal. Now our water. We know the specific heat capacity of our water is 4.184 joules per gram degrees Celsius. And the mass of our water, well, we have 425 milliliters again, so what's our mass? 425 grams. Can only do that with water, guys. The initial temperature of our water is 24 degrees Celsius. And what's our final temperature of the water?
42%.
42.7 degrees Celsius. It's in equilibrium, okay? And so our equation we're using is Q initial, we can call it, or whatever. Q of our metal equals negative, so this time let's have the negative on this side, negative Q of our water. Which one is really negative? Which one's losing heat, the metal or the water? The metal. So it worked because that's the way we did it last time. Maybe it won't work this way. Should we try it? Yeah, let's try it. Okay. Now, do you want to do one equation at a time? Should we try it that way? Anybody want to do that? Okay, let's try it that way. And again, when you're doing these, yeah, you can just all out and just go. Okay. So let's do Q of the metal is equal to MC delta T. So let's find out, can we find Q of the metal? No, we don't have the C. So okay, let's save that one for later. So let's do Q of the water is equal to the mass of the water, 425 grams, multiply specific heat of the water, 4.184 joules per gram degree Celsius. That's an 8. Times the change in temperature. Okay, we're going to have to calculate the change in temperature, which is something. I didn't calculate it. So 42 minus.
18.7 degrees.
Thank you. 18.7 degrees Celsius. And let's make sure the units cancel out appropriately. Grams to grams, degrees Celsius. So the amount of heat from the water is, I didn't calculate that either, because I didn't do it this way, but that's okay, we still can. 33,252 joules, or 33.3 kilojoules. Okay, we'll just leave it like that. Now, should we say that's negative, because of what this equation says, just to show you it doesn't matter? Okay. Okay, so that's our negative. And then, let's see. We still don't know C. Do we know Q?
Yes.
If the Q of the water is negative 33252 joules, then what's the heat of our metal? Positive 33252 joules. You with me? And it kind of just, okay, let's see. Equals M, and we're looking for, so no, we know the mass is 550 grams. We're looking for C, so I'll just leave that as C. Times the change in temperature is negative 42.7 degrees Celsius. Minus 110. What's that?
-68.
Negative 68 degrees Celsius. Does anybody see a problem?
We're gonna have a negative.
We're going to have a negative answer for our specific heat capacity. Now, why is that? Did the water lose heat? No, it gained heat. So do you see how that should have been positive? And it makes that negative.
So we put our signs depends on the initial and final temperature. If we see that it gained, it went up, so we put
Do you know how I did this when I was going to school? I just used my thinker. And I said, okay, I find an energy, just get rid of the negatives. Boom. Find my energy, and then if I get a negative over here and I'm looking for C, well, I can't get a negative. But here's the thing. What happens if we're looking for initial temperature or final temperature? That's where we get the negative, right? So you got to make sure you know where the negative is. Good? So in this case, we should have the negative on the other side. And that's why it worked out so smoothly last time, right? Anybody scared about that negative?
Is it just always on whenever it's losing heat?
Yeah, because that's what negative heat means, right? It's releasing heat. Okay? So later we'll talk about a cooling process, and we can use the same equation. And all right. So we can divide both sides by these, and here I should have solved for C before I plugged them in, right? Because now I have to deal with But we can still do it, right? Just grab our calculator, and I'll just type in a 33252 negative divided by 550, and then divided by 68 negative. And I'm going to get my specific heat capacity of the metal is 0.889. Oh, see, what are the units? What cancels? Nothing cancels. Grams in degrees Celsius under joules, so joules per gram degrees Celsius. We good? Yeah.
For these heat problems, it's always Celsius, right? Or
I
temperature. Never use Kelvin.
you could
Otherwise it'd screw up our student.
you could use either one. And just know joules per gram degrees Celsius is the same as joules per gram Kelvin. And why is it okay? Because we're talking about change in temperature, and the increments are the same for Kelvin and temperature. That's why. But generally, we use degrees Celsius. Why? Because we don't have a thermometer that measures in Kelvin. That's why. So generally, if there's a Kelvin in there, it's probably because some doctor dude says, "Oh, I'm going to make this hard." I'm sorry. I tell that to my wife, and she thinks doctors talk that way. When I say doctor, I'm not talking about a medical doctor. I'm just talking about somebody with a doctorate degree that wants to, yeah, I'm high and mighty over here. Sorry. That's what is that called? Stereotyping. I'm sorry. I apologize. All doctors aren't that way. But I remember going to school with a guy. He's going to be a math teacher. And he says, I'm going to get a doctorate degree and make everybody call me Dr. So-and-so. He didn't talk like that, but okay. Just and the kind of person he was, like, yeah, you would. You And I had a teacher when I was in high school. He was called Dr. I can't remember his name. And he was the same way. It's like, what is wrong with these teacher guys that are doctors? I never want a doctorate degree because then I'm going to be... No, sorry. I'm just teasing. There I go again. Okay. Breathe in. Breathe out.
Stereotypes exist for a reason.
What?
Stereotypes exist for a reason.
Yeah. All right. We good about stereotypes? Okay. So let's leave it that alone. All right. Any questions? I'm sorry if I offended anybody. Okay. Let's Move on to another example? Yeah.
Was that the second method you're talking about for the first example?
Yeah, so instead of solving for mass, we're solving for degree, the specific heat capacity.
Gotcha.
And this time, we're gonna solve for the initial temperature of our metal. Oh, this one's harder. Now there's a minus sign in there, right? So let's do this. Example 3. So we have, so here's our metal. The mass of our metal is 360 grams. And here's our water. It's dropped into 425 milliliters of water, so that means the mass of our water is 425 grams. You with me? So I'm just rating this and pulling out the information as I go. And this is how I would encourage you guys to do story problems. Write stuff down as you go. Have blank paper to show your work and make sure you're doing it right. Okay, so the initial temperature of the water is 24 degrees Celsius. And the final temperature of the water is, again, 42.7 degrees Celsius. It won't have to be that, guys. Whoever made these problems. What? Because I got these problems from the guy that, anyway, just to make it simple on my part. And that's what he used. But yeah, it doesn't have to be 42.7.
Is this one of those doctor guys you were talking about?
Maybe, I don't know. What is the initial temperature of the metal? So we're looking for initial temperature of our metal. Did you have, someone have a question over here? Carla.
Sorry, did you say that the mass of the water was given, or you have to find it?
So it was 425 milliliters of water. But we know the density of water is 1 milligram, or milliliter is equal to 1 gram, or 1 gram per milliliter. So that means they're the same. Okay, and it'll only work that way with water. But fortunately for these calorimetry problems, we use water. Why? Because we know everything about it, right? It's everywhere. Don't pick some substance that we don't know nothing about, right? Make it hard. And we know the specific heat of metal is 0.449 joules per gram degrees Celsius. We're dealing with iron again. And the specific heat of water is 4.184 joules per gram degrees Celsius. After doing a ton of this, if you guys do this whole worksheet, you guys are going to know the specific heat of water, right? All right. So let's find Tim. Initial temperature of the metal. Okay, how do you want to do this? Where should we start? Yeah.
Oh, wait, never mind. I was gonna say, we're not given the final for the metal, right, but we know it's 42.7.
Yeah. Oh, yeah. So good. We can say the final temperature of the metal is 42.7 degrees Celsius. Good. Yeah. Does everybody understand that? Okay. Do you want to put both equations together, or do you like to keep it separate?
Together.
Okay. We'll do majority rules. Who says put them together? Who says keep them? You gotta keep them separated. Okay. Okay. It was like one. So we'll keep it separate. It's one person majority. The rest of us doesn't care, right? Okay.
Don't do segregation anymore.
Oh, the next one we'll do together, just so you have practice. How's that? Okay. So what are we going to find first, water or metal? Water. We know everything about water. So we have Q equals MC delta T. Q equals MCAT, right? Good way to remember it. And we're looking for Q. That's equal to the mass of the water, which is 425 grams. Specific heat of water is 4.184 joules per gram degrees Celsius. And somebody calculate the change in temperature. 42.7 minus 24.
18.7.
Oh, is it the same numbers? Okay. All right, so we can see that all the units cancel out except for joules. That means our Q of the water is equal to, and again, I didn't do it this way. Somebody calculate that for me.
It's the same as before, right?
Yeah, it's 33.
Oh, is it the same numbers, right? What was it again? 30?
33.252 kilojoules.
252, and we'll just keep it as joules so that the units are the same and they cancel appropriately. Okay, now is that an exothermic process for the water or endo? Does water take in heat or does it release heat? It's taken in because the metal's hotter, right? Heat goes from hot objects to cold objects. The water's colder to begin with. So we're going to say that's a positive heat. Make sense? Okay. So that means the heat of the metal is going to equal what? Negative 33252 joules. And then that's equal to MCAT. And the mass is 360 grams. Specific heat capacity is 0.449 joules per gram degrees Celsius times the change in temperature. I'll just leave it like that for a minute because it's getting a little messy. I'm just running out of room. Again, I should have solved for it first. Would have been easier. Maybe I should do that. Let's do that. And if you don't like to do that, then don't. Negative 33252 joules. All right, so let's, we got Q equals MCAT. I almost put A there. All right. And specifically, let's put the equation for change in temperature as final temperature minus initial temperature. We good? All right, so we're solving for TI. So what do? Algebraically. Divide by MC to both sides. And so now we have Q divided by MC equals T final minus T initial. Now what? We could do...
Subtract over final and then multiply everything by number one.
Okay, subtract T final to both sides. And then we got Q over MC minus T final equals negative T initial. And then we're going to multiply both sides or just change all the signs, right? You with me? Okay, so this is our formula. And so it's equal to Q with a negative Q. Well, our Q is a negative number. That's nice. That negative goes away. So 33252 joules over M is 0.449 joules per gram degrees Celsius times, well, that's our C. Our mass is 360. And then we're going to add to that our final temperature, which is 42.27 degrees, 42.7 degrees Celsius. Let's look at our units, make sure they cancel correctly. So the joules cancels, the grams cancels, and we have degrees Celsius on the bottom of the bottom, so that's what our answer is going to be for this piece. And we do that, and we're going to get 248 degrees Celsius if I calculated it correctly. So I'm talking about this whole thing is 248 degrees Celsius. But you can find this part if you want, and you're going to get a number, then you can add it to this number. Right? And we have a positive hot value, and that makes sense in our mind. Well, it makes sense in my mind. How about yours? Okay? Yeah,
I'm just a bit confused on changing signs, because didn't we start with negative Q? So why would we like suddenly add a negative when it's convenient to make TF and T?
because we're using our thinker. So when the water goes through this process, does it gain heat or does it lose heat?
Gains heat?
Yeah, it gets hotter, right? It goes from 24 degrees Celsius to 42.7 degrees. So it's going to gain heat. That means it's a positive value. You with me? And according to this equation, Q equals negative Q. Q of the metal equals... So the Q of the metal is the opposite of whatever the Q of the water is. So the Q of the water is positive 33252. That means the Q of the metal is negative 33252 joules.
Right.
Make sense?
Yeah, no, I got that part. I'm just trying to understand algebraically how
How it just works out?
negative.
Oh, because you have another negative.
Because here we have T final minus T initial. I subtracted T final to both sides, and then I have it's equal to negative TI.
Right.
And so I multiplied everything by negative 1, and it got rid of that negative number.
But isn't it negative Q over MC minus TF minus TI equals minus TI?
Here, let me rewrite it. So this is what it was. Right?
Minus TI.
Why wouldn't it be negative Q?
Oh yeah, minus TI, sorry.
Why wouldn't we start with negative?
No,
Q?
yeah.
We knew that it was a negative. As well.
We could. I didn't plug this value in yet. I'm just solving it algebraically. I didn't put any numbers in. So, but this right here is what changes the sign and makes it appropriate. We good or no?
Yeah, I understand now. I was just confused because you didn't put the negative there, but
Yeah, I didn't plug it in until this last step.
right.
But once I did, this was a negative right here, and the negatives just go away.
Right.
Good?
Yeah, I just have to.
No, yeah, thanks for asking. Always ask. Don't drink it, it's gonna make you pee. Okay. Anything else?
How did you get 248? Like, I understand how you got the
So I'll type it in. So we got 33252 divided by 0.449 divided by 360. And then I got 205.7. And then I'm going to add to that 42.7. And I got 248.4. I just rounded 248.
Oh, because you add that because it's the final.
Yeah. Good? Thanks for asking. All right. Now we have the same type of problem. Actually, the next two are going to be even easier than that. It's just using Q equals MCAT. Okay. So we got hand warmer and cold pack. Which one do you want to do? Or do you want to do either? Because all we're using here is Q equals MC delta T. We're not using a calorimeter at all here. But I told you was going to do some more. If you want to do more of that, we can. We did it twice here. So basically, we're just using that same equation again, just one time. Who wants to do one? Okay, let's do it. Hot or cold? Let's do cold.
Yeah.
We dealt with a lot of heat. Let's do cold. So this is example 4. All right, so we have a cold pack. And we have 3.21 grams of solid aluminum nitrate, ammonium nitrate, NH4NO3, dissolves in, so here's our water, dissolves in 50 grams of water, so that's our mass. Oh, maybe we do two. We do both of them in this case. In the hand warmer, we didn't. Okay, so good. And the initial temperature of our water is 24.9 degrees Celsius. The temperature of the solution drops, so the final temperature is now 20.3 degrees Celsius. What is the heat of this reaction? Do we know anything else that's not up there? Yeah, the specific heat of water is 4.184 joules per gram degrees Celsius. So can we calculate heat using this value right here? Yeah, we can figure out how much heat is lost without doing anything with this over here, can't we?
So it seems like the cold pack stuff is irrelevant to what the problem's
Yeah.
asking.
Unless we wanted to know the specific heat of the ammonium nitrate, right? Okay. But in this problem, we're not looking for that. So this time is, let's see what happens. So Q is equal to MC delta T. We're already solved for Q, so that's good. We don't have to do anything. The mass is 50 grams. Specific heat is 4.184 joules per gram degrees Celsius. And what's the final temperature, or the change in temperature?
-4.6.
Negative 4.6 degrees Celsius. Thanks, Milosh. Okay. And, we're going to get a negative value. Does that make sense why we get a negative value? Yeah, it's getting colder. We're losing heat. Okay. So our heat of our reaction of 3.21 grams, which was just extra information, is equal to negative 962.32 joules. We can write our answer like this, or we can say Q of reaction, or we could just say, rather, 962.32 joules released, or hold on a sec. This is absorbed from the surroundings, right? Isn't that what a cold pack does? It takes in the heat from the surroundings, therefore making the surroundings feel colder.
So then now, like, the Q of the cold pack would be positive, and the Q of the water would be negative. I know it doesn't technically matter, but
Yeah,
yeah, it's just
yeah.
how you think
Yep.
about it.
Questions?
So that's why cold packs stop working, because they're absorbing the heat from the surrounding area, right?
They probably stop working is because they're all the way reacted. They're done reacting, and then what happens? It reaches equilibrium after a while. Yep. Oh, perfect time. Any questions on this? Fun, right?
So we didn't at all.
You guys, this is for you. I give you guys plenty of practice. You're welcome. Sorry, what's your question?
We didn't at all have to use the weight of
Yeah, we didn't.
nitrate.
Because it asked for how much heat was lost, or how much heat was lost from the surroundings, really, right? Or, sorry. Yeah.
How would that be worded, what it was asking for? Like how much?
So it says what is the heat of this reaction? So we actually, yeah, it should be a positive value. Right? Am I thinking backwards? So we got heat. No, yeah, it's negative. It's released. Right? Because, now I'm confusing myself. It's absorbed. Because, sorry about that. Because when you grab the cold pack, you feel cold because what? It's taking the heat from your hand. Yeah. So, yeah. We good? All right, take a break. Okay, we got just two more example problems, and then we'll talk about bomb calorimeters, and then be done. I think that'd be enough. Because we are on schedule again, so that's nice. I hope next time doesn't take too long. I hope we don't overdo it there. So, but okay, let's do another example. Example 5. So, melting ice in water. Okay, we have a flask that contains a mass of 250 grams of water at an initial temperature of 20 degrees Celsius. And if we add, so our ice over here, if we add 8 grams of ice to the flask and let it reach equilibrium, we want to know, well, what is the change in temperature of the whole system? Well, I guess I should put that over here. We also need to find the final temperature, right? And then we need to know, is any ice left over? So a few questions here. So there's another value we have to know. The heat required to melt ice is 333.6 joules per gram of ice. And we know the specific heat of the water is still 4.184 joules per gram degrees Celsius. Good?
That Q value is what? The amount of.
And this is the heat required to melt ice. 333.6 joules. So this isn't necessarily the Q. What should I call this? This is for melting. Actually, this is, you talked about the phase change. This is like the heat of fusion, right? Or heat of fusion. So that's given to us. So let's, that's not the heat that's in this equation. Yeah? We're not necessarily looking for that, but here we go. If we want to know the heat, what do? 333.6 joules per gram, and we are melting 8 grams of ice. Mm-hmm, it is. But we'll see what the numbers look like in the end. Okay, so that's gonna give us 2,668.8 joules. And that's the heat gained or lost.
It'd be gained, 'cause we moved the ice.
Gained by the ice, right?
Mhm.
Lost by the water. So Q of the ice is 2,668.8 joules positive, right? And that means Q of the water is a negative 2,668.8 joules. You following? Okay. All right, so let's find change in temperature. That'd be easiest to find if we have Q equals mc delta T. We just solve for delta T by dividing both sides by mc. And so delta T is equal to, the change in temperature of our water is equal to a negative 2,668.8 joules divided by the mass of our water is 250 grams, and the specific heat capacity of water is 4.184 joules per gram degrees Celsius. Joules cancel, grams cancel, we're left with degrees Celsius, and we get the change in temperature equals negative 2.55 degrees Celsius. So that means our temperature lowers to what? 20 minus 2.55 degrees Celsius is 17.45 degrees Celsius. So is there any ice left?
But we solved it assuming that there's not gonna be any ice left, so.
But what temperature did we get? Above freezing point. So do we have any ice left? No. If that was a negative temperature, then we probably wouldn't dissolve, it wouldn't melt all the way. Yeah.
How did you know to put the negative 2,668 joules? Cause aren't we solving for the change in temperature of melting ice? Oh, melting ice, which is water.
So
Right.
melting ice, so this part right here, the Q of ice, we take this value right here, the amount of energy per gram of ice, and we multiplied that by 8, and we got this value. And what happened to the ice? Did the ice take in the heat or did it throw out heat? If it's melting, it has to take in the heat.
But
Has
I'm
to
saying,
abs-
why do you use to find this, is it because you're, like, why do you use the negative if you're trying to find the changing temperature of the ice?
Because the water is the surroundings. So if that means the ice had to take in the heat from the water.
Sorry, yeah.
No, don't be. Are we good?
Can you explain one more time? You lost me when you were talking about how we know that there's no ice left.
Okay. Our final temperature of our water is 17.45 degrees. Well, is that solid ice? Is that solid water or liquid water at that temperature? What temperature does water freeze? 0 degrees. Since it's above 0 degrees, yeah, it melted. Because we're done.
And this problem, it's like we added 8 grams of ice drawing the water melting ice up there.
The water, no. You mean the cube of ice?
No, I was just confused by like the nomenclature we were using. But like, I'm just trying to figure out how this to be worded. So like an example here, it says like 250 grams of water at 3 degrees Celsius is mixed with 40 grams of ice. And so that's pretty much how it would be written.
Yeah.
Okay.
Yep. We good on that? Okay, now next, the last example before we move on to the last topic is, what if we have two things of water, different temperatures, and we put them together? They're going to still reach equilibrium. We want to know what that is and how much heat is lost by one and gained by the other, right? All right, so container one, so we'll just call this number 1 and number 2. So one flask contains a mass of 150 grams. Initial temperature is 20 degrees Celsius. And the second has a mass of 350 grams and an initial temperature of 98 degrees Celsius. What is temperature final after the two flasks are mixed? So we want to look for temperature final, which is the same for both. Does that make sense in everybody's mind? Okay, they're going to reach the same final temperature. And we know the density of water is, well, we don't need to know the density of water in this case. We know the specific heat of water is 4.184 joules per gram degrees Celsius. All right, let's combine these equations to make it be Q gained equals negative Q lost, we can call it, or Q of 1 minus Q of 2, right? So that means it's going to be M1 C1, which is just C, times T final minus T initial 1 equals M2C times T final minus T2 initial. Well, I need to put a negative on one of those. I'll put it on this one because this one's going to lose the heat, right? You with me?
Is this, I'm sorry, I spaced out. Is this two solutions of water at different
Yes.
degrees? Okay.
Yep, that's all it is. So they both have the same specific heat, and they're going to both have the same final temperature. That's why I use the same variable in this case. All right, let's simplify this before we do anything else. You see how we can divide both sides by C? We don't even need that because they both have the same specific heat capacity. So will it always be the same? No, if you're putting water, mixing it with soda, they're not going to have the same specific heat capacity. Okay? Barely not, but okay. All right, so we are looking for the final temperature. Let's combine these algebraically. So I'm going to add to both sides. No, I'm not going to add. We'll just distribute. Does that make sense to everybody? Put them all together so that we have terms. So M1TF minus M1T1I equals negative M2TF minus times the negative is a plus M2T2I. Any questions on how I got that? We good? All right. So now let's put terms together. let's put both of the TFs together because that's what we're looking for, right? So we're going to add M2 TF to both sides. And then we're going to add M1 T1I to both sides. And that gets rid of all the negatives. That's nice. Any questions on that step?
This is just to eliminate negatives.
No, it's to get TF on one side all by itself. We're just using algebra, solving for TF. Do you follow my steps?
I think I need to see what this does.
Okay. Do you understand the rules of algebra that I'm using, though?
Yeah.
Okay.
It's just a lot of,
Yeah, there is a lot. So this is going to be M1 TF plus M2 TF is equal to M1 T1I plus M2 T2I. And I'm doing this before I'm plugging any numbers in. If you like numbers, then do it. But anyway, try it both ways and see which way you like, and then do it the way you like. All right, so we can factor out a TF, yeah? M1 plus M2. That side stays the same. So now let's divide both sides by M1 plus M2. And this is my TF. There's my formula. And now I could just plug and chug. Any questions on that?
could you explain again, why we eliminated C? It was on both sides.
Yeah, because it is on both sides. We can keep it there if we would like, but then we're going to multiply everything by C.
Right.
And then over here, we would have this C over here, and we would have a C over here, and what happens? It cancels out anyway.
So we're saying since it's the same value, we can just
Yeah.
divide it. It makes a 1. And
Yeah.
just ignore that.
Yep.
Okay. Gotcha.
Good? Anything else? All right. So now our TF, now we got to plug our values in. You guys have the values? Because I have them right here. I know you can't see them on the board. That's going to equal M1, which is 150 grams, times the initial temperature of our first flask is 20 degrees Celsius, plus M2, which is 350 grams, times the initial temperature is 98 degrees Celsius, all over M1 plus M2, so that's 150 grams plus 350 grams. And we math it out, and we get 74.6 degrees Celsius. And if you look at your answer, it's between 20 degrees Celsius and 98 degrees Celsius, and it should be. What should it be closer to, 98 or 20? Why? Because there's more of the 98, right? So it should be closer. So just kind of look at that and make sure, okay, does it make sense? Or does that make sense to everybody? My way of thinking? Okay. That's it. Could we then calculate the amount of heat lost and gained? We could. In this case, we don't care, but yeah.
And I understand why you didn't, but you could also solve this by keeping all of the, like the coefficients with numbers in there, right? Where you have the individual variables. And just leave like, you know what I mean, like 150 grams.
Put the numbers instead of the variables?
Yeah.
Yeah, definitely.
Okay.
it just gets kind of messy that way.
Right,
But again, if that's more comfortable for you,
sure,
go for it.
okay.
No problem. Just be careful, because it does get a little bulky.
It's way easier symbolically.
Yeah.
As soon as you start throwing the numbers, it's so much easier to make a mistake.
Yeah. I remember I took, did I tell you guys I took physics for engineers and that's where I learned it from? I tell you that? Okay. And I was the same way. I was like, whatever, I'm gonna plug numbers in first, because that's the way you do it growing up in grade school or high school or whatever, right? Anyway, yeah, it's
Tell them it's a
try it anyway. Try it a few times before you throw it out. All right, any questions on the MCAT equation? All right, let's move on to the, so we use Q equals MC delta T when our temperature stays pretty consistent. But when our volume stays consistent and our temperature changes, then we use a bomb calorimeter. You guys ever make a bomb? Maybe a dry ice bomb or something? Yeah, don't, but, okay.
Usually I use pipes.
Okay. You put some dry ice in a bottle and you put the lid on, what happens? It builds pressure, but the volume doesn't change. So what happens? Bomb, right? Okay. So that's why we call it a bomb calorimeter, because the volume stays consistent. So let me just draw a little diagram. Maybe I shouldn't draw it. Okay. So a bomb calorimeter. Okay, well, that was weird. Let's see if I have a picture here. Good. Okay. So in here, this is our surroundings, and this is our bomb. So this is a little container inside. It's kind of like our metal that we throw in there, right? And we have our chemical reaction going off in here, and it produces heat. The heat transfers to the metal and then eventually kind of goes into here, right? Does that make sense, kind of-ish? Any questions on what a bomb calorimeter is? All right. So this time we have our reactions inside here. So this is our reaction. And the heat of our reaction is going to equal negative the heat gained by the water plus the heat of our bomb. This is our bomb. Are we good? And to calculate the heat of the bomb, this is also on your reference sheet. Yeah, in fact, so is that other equation, the Q equals MC delta T. So this is equal to the heat capacity of the material of our bomb itself. Okay, so it's not a bomb, guys. It's our container that holds the reaction inside our calorimeter. So the heat capacity of our bomb, and remember, heat capacity is joules per degrees Celsius, right? Do you remember learning about that last time? Okay. Multiplied by a change in temperature. So again, I'm going to write right here, this C is our capital C, or this is our heat capacity, not specific heat capacity. So it's a little bit more of a calculation, but still not too bad, yeah.
What is the N? The heat of N?
That is, sorry, water,
Oh,
W, my bad. Yeah,
So, silly question, what exactly does Q mean? Does Q just mean heat?
uh-huh,
Okay.
yep. Did you have a question, Olivia?
It was the,
Oh, okay. I just learned to write better, huh? Okay. I know how to write better. Did I tell you guys this? Did I? Okay, it's my last class because I have the same problem in that class. They just can't read my stuff. Okay, when I was little, I had great handwriting, and then what happens?
Go to school.
You go to school and then you have to hurry, write it. I got to get all this information right. Sorry, girls can just have good handwriting anyway, so I don't know what it is. Okay.
Better than me.
Yep. You guessed that. Okay. All right. Let's do an example. So we have when 3.12 grams of glucose, C6H12O6, is burned in a bomb calorimeter, the temperature of the water increases from 23.8 degrees Celsius to 35.6 degrees Celsius. The calorimeter contains a mass of 775 grams of water, and the bomb itself has a heat capacity of 893 joules per degree Celsius. How much heat is produced by the combustion of glucose? So this is the heat of reaction. So Q of the reaction is equal to negative Q of the water plus Q of the bomb. Okay, so let's find Q of the bomb.
What is it that the problem was asking for? The total? Q bar?
The heat of reaction.
The heat of reaction.
How
that's
much
just for the
heat-
C6, 8, 12, whatever.
Well, yeah, this reaction goes off, and how you find it is, well, it heats up the bomb, which then heats up the water, right? But does all that temperature have to go into the water? Maybe not, right? So that's why this is the formula. And so let's find heat of the bomb. Did I answer your question?
I mean, maybe, but I still don't understand. So I guess no?
Okay. Let's go through it and see. Okay. So heat of the bomb is just going to be 893 joules per degree Celsius times the change in temperature, which is 35.6 degrees minus 23.8 degrees, which is 11.8 degrees Celsius. And we get that's equal to,
Wait, how do you do that without adding the math in?
because the heat capacity doesn't have mass. Do you remember the difference between a heat capacity and specific heat capacity?
But I mean, to find Q bomb, wouldn't it be mass times C times?
No. because Q bomb is equal to the heat capacity times the change in temperature. Because heat capacity is joules per degree Celsius times the change in temperature is degrees Celsius, and we just get joules. Good? And so we're going to get the Q bomb is 10.54 kilojoules. Or we can just keep it in joules for now. 537.4 joules. Good? And then the heat of the water, this, we have to use MC delta T, right? So the mass of the water is 775 grams, and the heat capacity of water is still 4.184 joules per gram degrees Celsius, times the change in temperature is still 11.8 degrees Celsius. And all those units cancel out except for joules, and we get 38.26 kilojoules. So since we can use kilojoules, because they're both kilojoules. You follow me so far? So the heat of reaction is equal to a negative heat of water plus heat of the bomb. So that's equal to negative heat of the water is 38.26 kilojoules plus heat of the bomb is 10.54 kilojoules, making the heat of the reaction negative 48.8 kilojoules. So this equation right here is not on your reference sheet. So you might want to stick that on your reference sheet.
The individual parts on the reference sheet?
The bomb, the heat of the bomb and the heat, yep. Both of those are on there. We good? Okay. If you want more practice, here it is. I'll post the answers as soon as they're finished. Yeah.
So since Q equals joules, we don't always have to solve it with MCAT, we can just solve it based off of the heat capacity if we have. Multiply it by the.
If you have the heat capacity of an object, but if you have just a certain amount of water, you're not going to have the heat capacity of that amount of water. Otherwise, they'd have to make a heat capacity for infinite amounts, right? So for water, for example, then we're just going to give you the specific heat capacity of water.
And that's because we can cancel out the units, and that just leaves us with joules.
Uh-huh. Anything else?
So, in the equation, when we use MC delta T, that's the specific heat capacity?
That's the specific heat, the C in that, yes.
When dealing with the Q bomb, that's the heat.
That's the heat capacity. Yes. And you can kind of see right here, just by the units, heat capacity is joules per degree Celsius.
The other one is-
Specific heat capacity is joules per gram degree Celsius. Depends on how much you have. This just depends on the object.
Oh, and that's why we can use heat capacity, not specific.
Yeah,
The
and,
other way
and
around.
to find the heat capacity, you'd have to find it for each object. And we don't really do that. We
Right.
don't have a table for every object in the universe. But when we do bomb calorimetry specifically, they probably calculate the heat capacity of a bomb, right? And then we know what it is for that bomb. Then we can use that for a lot of different reactions.
And if we were to try this, like with specific heat capacity, with the shorter equation, it would just leave us with joules per grams, which is nothing, right? Like it wouldn't come out to anything.
Yeah, if the units don't cancel appropriately, something's off. Yep. Always use units, guys. It's your way to be good at chemistry. Okay? We still have 27 minutes. Do you want to do anything?
Make a bomb?
Can you show us how?
I told you how, yeah. But if you decide to do that, be careful and don't hang on to it and say, hey, let's see who can hold it longest. No, don't do that, okay?
I made it through the 4th of July. We saw Pioneer Day.
All right, have a fantastic weekend.
The container,
Oh, yeah.
container B. I did the whole thing.
Is
And
this
I-
the two waters?
Yeah,
Okay.
and I just got, this is what you got, and that's what I got, and I just can't figure out why.
Oh, really?
Like where I'm
Like 1 and 2?
messing up.
Let's, and let's make sure we have the same numbers, because
Yeah, that's